Hello everybody, and welcome to an extra lecture segment of 6838. While we were watching the previous lecture video, I realized that the example I gave you of variational calculus was pretty darn complicated, so I thought I would record an extra segment that went through a simpler example first. My apologies for that. I'm also going to share on the course webpage my own handwritten notes, at least, that really walk through this calculation carefully. So the problem that I thought would be kind of fun to derive variationally is to give some interpretation for the space of cubic splines. And this actually relates to my 6837 intro graphics class, which spends quite a bit of time figuring out how to compute cubic spline curves in practice. So in case you all didn't take my undergrad course, or you need a little bit of a refresher, we're going to specifically motivate or meet splines, which are derived from sort of the following boundary information. The basic idea of a spline is that I want to use it for an interpolation problem. So let's say that I have some unknown function f of t, which is a function of time t. The basic kind of use of a spline is to say, if I know something about f of t at some sparse set of t samples, I want to come up with a reasonable interpretation or interpolation of the data in between. So in particular, what we're going to assume today is that we know the value of a function at time 0, and specifically at time 1, just because I'm a little bit lazy. And moreover, we know the slope of our function. So maybe it looks something like that. Okay, and our goal is to fill in some reasonable interpolant function f of t that has these prescribed values and these prescribed slopes at these two locations. So maybe something like that. I'm not a very good artist, as we'll see. So in particular, we can think of our input data as follows. Essentially, we're given four things. We're given that f of 0 equals some value a, right? So there's a. We're given f of 1 equals some value b, so that's roughly b. And moreover, we've prescribed the slope at 0 and 1. So we know that f prime of 0 is equal to some value c, and the f prime of 1 is equal to some value d. So this is all of the information that we know. And what we want is some reasonable interpolant f of t. Now, of course, the word reasonable here is totally vague, and we need to give it some more information in order to make our problem well posed. And I think that a typical ansatz that people make when they're designing these sorts of interpolatory schemes is basically to ask that their interpolant is smooth in some sense. Or maybe kind of an interpolant that is as close to being a line as possible. But of course, it's impossible to be exactly a line because maybe I've prescribed two incompatible slopes c and d, right? And a line, of course, has constant slope. So here's one way to make this a little bit more formal. Now, recall a sort of basic fact from calculus, which is that f of t is a line if, in fact, if and only if, assuming that f is differentiable, I guess, the second derivative of f is identically equal to 0. So let's think about kind of a funny problem, which is, let's say that you give me a function f, specifically just on the unit interval from t equals 0 to t equals 1. You could ask kind of how line-like is this function f of t? Right? And somehow what we want to do is to find an f of t that is as close to being a line as possible. Now, there are a lot of different ways to measure that, but here's a very simple one, which is to say, okay, well, somehow a function that looks a lot like a straight line is one whose second derivative is close to 0. That's debatable, but it's some model. And if you buy into that model, then here is a reasonable energy function which takes as input some function f of t, and what it's going to output is a scalar, which is some measurement saying how close f is to a line. In particular, I can use the letter E to stand for energy, which inputs a function, and what it's going to output is the integral from 0 to 1 of f double prime of t squared dt. So this is kind of a weird energy functional. First of all, when I use the word functional, the reason I'm saying functional instead of function is to sort of distinguish E from F here. So the idea is that the input to E is a function. It's not a vector of values. It is an entire function on the unit interval from 0 to 1. Now, many students in this course are graduate students who have seen advanced mathematics and would worry about things like, okay, but what function space? For our course, we're going to essentially make as many smoothness assumptions as we need, and similarly for existence. I'm less concerned about the formal argument and more that you guys get the intuition for what variational calculus tells us about life. So it's perfectly fine here. We're going to assume that f is smooth. Later on, we're going to minimize our energy, and we're also going to assume that a minimum exists and is sufficiently differentiable. This would be totally non-kosher in a math class, but we're going to do kind of physicist, computer scientist style reasoning here just to come up with a useful formula. Okay, but in any event, our energy function E inputs a function and then computes this integral from this function, right? So it computes the second derivative of f, squares it, and integrates that value from 0 to 1. Okay, so here's one thing that's kind of nice to know is that, well, if f is a line, well then f double prime is identically equal to 0, so when I square and integrate that from 0 to 1, I'll just get 0 for my energy. And as our function f becomes more and more wiggly, right, it gets more and more second derivative, then this energy gets higher. So somehow E is a reasonable measurement of how far a function f is from being just a straight line. Now, if you're willing to buy that, and of course there is a little bit of modeling involved here, then you might ask an interesting optimization question, which is as follows. You can say, okay, remember our original problem is that we don't actually know the function f, we just know a few things about it. We know its value at time 0 and time 1, as well as its derivative. And our job is to fill in a reasonable interpolant in between. Well, here's one way that we could do it that looks an awful lot like optimization language that you've probably seen in calculus class or algorithms or many other different contexts. Essentially, what we can do is we can say, okay, well, let's try and minimize. But what is our variable here? Well, this is where things get a little bit funky, or at least a little different from what you're used to from your undergrad calculus class. Our variable, like the unknown object here, is an entire function. It's not just a vector of values, unless you're willing to make the conceit that it's somehow a vector of values at every, where the value is at every single t. But in any event, we can think of it as an optimization problem for a function on the unit interval into the real numbers. And again, we're going to assume that such a minimum exists and that it's smooth and whatever in this course. I know that that's not kosher. If you're interested, I can point you toward more mathematical treatments that give the details, but both in our discussion and on your homeworks, it's okay to be a little sloppy here. In any event, we're going to say, okay, well, I want the smoothest possible f, so I'm going to minimize this energy functional that I just cooked up, subject to some boundary constraints. Namely, I know that f of 0 is equal to a, f of 1 is equal to b, f of 2 is equal to, sorry, f prime of 0 is equal to c, and f prime of 1 is equal to d. Okay? And essentially, here is an optimization problem. Turns out it's well posed. We haven't proven that, but that's okay. That essentially what we're going to say is over all functions that have prescribed values at t equals 0 and t equals 1, as well as prescribed derivatives at t equals 0 and t equals 1, find me the function f that makes e the smallest. And of course, the space of unknowns here is humongous, right? I mean, it includes functions that, do all kinds of crazy stuff and then align. And it includes that nice smoother object that we had before. So now the question is, how can we solve an optimization problem when our variable is a function? And that's a really critical problem to think about quite a bit, because essentially it's going to come up all over the place when we talk about geometry, right? We're going to talk about lots and lots of optimization problems whose unknowns are shapes. And so let's use this nice cubic spline problem as a way to motivate that. Incidentally, as a quick aside, the term spline here comes from woodworking. I motivated this energy by just saying I want a function that kind of looks like a line. A very different way to do it is to think about taking a piece of wet wood that can bend and putting two nails in that wood at these 2 points and then bending it to align to those tangents. And then it turns out that the rest shape of the wood, like the one that's the least physical energy, actually will minimize exactly this objective. So there's your trivia fact for the day. Okay, so there's our basic setup. I'm going to clear this out and give ourselves a little bit more space to write. And our next question is going to be to try and draw an analog to finite dimensional calculus. Okay, so the way that we're going to figure out how to optimize this energy functional E is to draw an analog to the finite dimensional case. So let's think about the finite dimensional case of our problem a little bit. So in the finite dimensional analog, what are we trying to do? We're probably going to try and solve some problem that looks like this. Now, instead of having an unknown function f, maybe now we just have an unknown vector x in Rn, and we have some objective function g of x. And assuming that we want to apply machinery from calculus, probably what we would do then is to take the gradient with respect to x of g and set it equal to 0. And now the question is, can we do some analog of take the gradient and set it equal to 0 when our unknown isn't a vector, but rather is a function like this f here? So that's going to be the sort of analog that we're trying to draw. But that's a bit tricky, right? Okay, so what even is a gradient? Well, it's a vector of derivatives in individual directions, like in the x direction, the y direction, and the z direction, if n is equal to 3 here. But here we've got an infinite number of directions, right? There's a different unknown value, f double prime, or f rather, at every single possible t. And so this analog gets a little bit tricky to carry out. But one thing that we can do is modify it ever so slightly and find something that actually we can come up with an infinite dimensional analog without a whole lot of work. So here's going to be my trick. So if I want to minimize a function g of x, I can take its gradient, set it equal to 0 under some differentiability assumptions. And remember that the gradient here is a vector. Now, when is a vector equal to 0? Well, one really complicated condition, which seems overcomplicated, but actually is the one that's going to work better for us, would be to say, okay, well then, if I take any other vector v, and I take its dot product with the gradient of g, being evaluated at x, I get 0 for all vectors v in Rn. Right? That's to say that a weird condition for a vector to be equal to 0 is that its dot product with any other vector gives me 0 back. Okay? So these two are just equivalent conditions that I think you all could derive easily enough. Now, if you stare at this quantity here, you may actually recognize it. This is known as the directional derivative of the function g. Essentially, the directional derivative is saying, okay, so if I draw the level sets of g, and so maybe here n is equal to 2, so we're in the plane, like that, right? And if I'm at a local minimum x, then essentially what this quantity here is on the left-hand side is that I draw some vector v, and it's the rate of change of my function on the plane, but just in the v direction. In fact, I can write this in a different way. This is equivalent to the following, which sort of exposes this directional derivative formula by writing this kind of complicated looking expression. D over dh of g of x plus hv evaluated at h equals 0. So these two quantities are the same, this one and this one. Let's make sure that you can figure out why. So for one, it's just a chain rule exercise to convince yourself that these two things are equal to one another. But let's make sure that we can interpret this. So here h is a scalar and x and v are vectors or points. So in fact, if I want to be pedantic, I could put my little vector hats like that. So what is this saying? This is saying that I'm going to sit at some point x, which I think is a local minimum, so that's why I'm getting 0 on the left-hand side. And I'm going to take an arbitrary direction v, right, pointing out of x. And I'm going to kind of look at the restriction of our function g through x in the v direction. Okay, so it's kind of like taking this little slice of space through our function g here, and just writing it as that function. So here's like h. And then what is the plot of our function? Well, remember that we're assuming that x here is the point that minimizes our function g. Well, so when h equals 0, I get some value, and that's g of x. And it's the minimum possible value, right? So if I change h around, right, so as I move along this line here, and I record the value of g, well, I know that it kind of has to increase. Okay, so that's our condition, right? So hopefully you guys can understand this chain of logic. If not, I would pause this video for a minute and really try to digest this. That if I'm going to minimize a function g of x over vectors x, well, one way to do that is to take the gradient and set it equal to 0. The gradient being equal to 0 is the same as saying that the gradient dot product with any other vector v is equal to 0. And that is the same as computing this directional derivative, which is like the rate of change of our function in some one-dimensional slice. So here, I think the right intuition is that you can think of v, I'm having trouble with this pen. I can think of v as like a perturbation of x, right? So, or like a perturbation direction, really. This is supposed to be L-I-K-E, in case you were wondering. But anyway, the basic point here is that I can think of v as some direction where I'm going to take an infinitesimal change to x, and essentially what this expression at the bottom is saying is that if I make any infinitesimal change to x, well, then my objective had better increase if x is optimal for my optimization problem. And so one thing that's worth knowing is just that all these arrows go in both directions. So these are all just equivalent conditions. Okay, minus, going from min to setting the gradient equal to 0, which, as we know, conflates minimum, maximum, and saddle point. But we won't worry about that for now. Okay, so that's our finite dimensional story. And the basic point here is that taking the gradient and setting it equal to 0 is a little bit tricky in our infinite dimensional context, but setting directional derivatives equal to 0, we're going to find is a lot easier. So let's actually carry that out. Okay, so now our goal is to carry out an infinite dimensional version of that finite dimensional story that I just told. So let's see that we can actually do that. In particular, what we're going to introduce, in addition to our function f of t here, is a second function, which I'll think of as a perturbation. So we'll call it p of t, where p is for perturbation. So perturbation p of t. Okay, so here's going to be the big idea. The big idea is that we have some function, f of t, like what I've drawn for you here, which I think is optimal for my constrained optimization problem. I'm sorry I've erased the constraints, but hopefully you remember them. So what does that mean? That means that now if I take my function f and I edit it in some way, like maybe I introduce some bump, then my energy is going to increase. So I'm going to think of my bump as a function p of t. So the bumped version of f is going to be f of t, where again, t is the horizontal axis, plus h, which is like the magnitude of the bump, times p of t. Okay, so h is kind of controlling the height of the bump here. When h is equal to 0, I'm at my optimal function f. And as h increases, I'm making f more and more suboptimal. Okay? So what we really quickly introduced in lecture, a little too quickly, I'm sorry about that, is an object which is actually just the directional derivative with a new name because we're in this infinite dimensional case. Now in lecture, we called this the Gateaux derivative. Pardon my French. Or sometimes this is known as the variational derivative. This is related to the Euler-Lagrange equations, if you're used to that. Although I usually find that the Euler-Lagrange equations are just easier to derive from scratch than remember. Okay, so the Gateaux or variational derivative is just the directional derivative of our energy functional E evaluated at f, so f would be like our point x in that finite dimensional story, in the p direction. Okay? I'm going to keep rephrasing this 100 times because I think it's hard to get it in your head the first time. But again, the idea is that I want to know the rate of change of our energy functional as I take a function f and perturb it by adding a tiny bit of a function p. So we can notate that as dE centered at f in the p direction, like that. And just like the directional derivative, you can convince yourself that it has to be linear. But this can be defined in many different ways. Officially, the definition that we gave in class looks something like this. You can say it's d over dh of E of f plus h times p evaluated at h equals 0. So again, I can't emphasize enough how annoying it is to unpack this expression. But just to make sure that we're all on the same page here, remember that f and p are functions, and h is a scalar. Okay, so the idea, again, is that I start at some function f, and I introduce a tiny amount of a function p, right? It's scaled by the scalar h. And I want to know the rate of change of our energy functional as I introduce that perturbation. Now, our energy functional is a complicated thing, right? It inputs a function and outputs an integral. But the kind of nice thing is that if I think of this as a function of h, well, now it's something that inputs a scalar, h, and outputs another scalar, right? So we're down to the one-dimensional case, and that's something that we can work with. So since we're in this digital format anyway, I really would encourage you to pause here and just make sure that you're following. I think that this is one of these expressions that is totally natural and makes perfect sense for the application that we care about. But the first time you see it, I think this expression is just really hard to parse. So think about it quite a bit. You know, ask questions on Piazza as you need, and I think you'll figure it out. Okay, so what I've written here is the definition of the Gateaux derivative. But now let's actually compute it for our energy functional E, for this specific choice of E. Okay? So starting with this equal sign, I'm intending it to be not the general definition of Gateaux derivative, but specifically for this choice of E. Hopefully you all follow. But in any event, in this particular case, to fill in some detail, what is this? It's d over dh. And now I have to plug in f plus hp for the input to our energy functional E. And so we can do that by just following the form on the right-hand side. So this is the integral from 0 to 1. And now we have to be a little bit careful here. So prime is denoting differentiation with respect to t. Okay? And what is it differentiating with respect to t? It's differentiating the input to our functional e. In this case, the input to our functional isn't just a function f, it's f plus hp, where f and p are functions of t. That was a lot of letters. But in any event, what I'm going to get is f double prime of t plus hp double prime of t dt. Okay. Now, all of this is evaluated at h equals 0. Okay, so all I did was I took the general definition of Gateaux derivative and plugged in our particular choice of energy functional. All right, so now we have to do a bit of a calculus exercise to simplify this ugly-looking expression. We're going to make use, almost always when we compute these derivatives in 6838, of a particular formula called differentiation under the integral sign. This is included in that formula sheet that I distributed on day 1. But the basic high-level point is pretty straightforward. Basically, notice that our integral is with respect to t, our derivative is with respect to h. And so differentiation under the integral sign just says that you can exchange these two things. So I can move the d over dh inside of the integral. That's perfectly fine. Okay, so in that case, oops, I forgot to square. Well, now I can apply the chain rule. Now, the primes are derivatives with respect to t. Now I'm differentiating with respect to h here, so I can think of these just like constants. So what am I going to get? I'll get that this is the integral from 0 to 1. And now let's, I guess, apply the product or rule. Actually, the chain rule is okay. So we can do 2 times f double prime of t plus hp double prime of t times the derivative of the inside with respect to h, which is just p double prime of t dt, evaluated at h equals 0. If that went by a little fast, I encourage you again to pause the video and convince yourself that these two things are equal to one another. And finally, let's plug in h equals 0, and I'm going to get kind of a nice inner product. So this is just equal to 2 times the integral from 0 to 1 of, well, now h is equal to 0, so this term vanishes. And I get f double prime of t, p double prime of t, dt. Okay. And there's our Gateaux derivative. We have a closed form expression, right? So what does it do? At least when p and f are differentiable, it inputs a p and an f, and it gives you back basically the inner product between their second derivatives. Okay. So in this course, there's like a really reasonable thing that essentially you should just always do, which is like if you're ever in doubt of what to do next in 6838 or in life, you should integrate by parts. Okay? And that's exactly what we're going to do next. So we're going to take this expression, and just almost always when you're working with variational calculus, kind of a good thing to do is to try to isolate the variation direction, like p here, without any derivatives in front of it, if you can. So here we have p double prime. It'd be nice to get rid of the double primes here. So in fact, it turns out that we can do that. Okay? So if we integrate by parts, then what are we going to get? Well, let's continue our math over here. So this is equal to, well, if we integrate by parts one time, we can pop off one derivative from p and put it onto f here. So we'll get, let's see, 2 times f double prime of t, p single prime of t, evaluated at 0, 1, minus 2 times the integral from 0 to 1 of f triple prime of t, p prime of t dt. This is just integration by parts in 1D for once, so it's actually the integration by parts that you're used to. Let me check my notes and make sure that they agree. So 2 f double prime p prime minus 2 f triple. Yep. Okay. And now we're almost there, at least in the integral. The boundary terms we'll see we can ignore. But in any event, Okay, let's get rid of this first derivative on p by integrating by parts a second time. So what do? We get 2f double prime of t, p prime of t, evaluated at 0, 1, minus, okay, well now we're going to get, what, 2f triple prime of t, p of t, evaluated 0, 1, plus the integral of the fourth derivative of f, evaluated at t, times p of t dt. Now, why did I just go to all that work? Like, if you kind of remember from our finite dimensional case, right, we were kind of after like the inner product between v and the gradient, right? The directional derivative in the v direction of our function was just v dot the gradient. Well, take a look. Now we have some inner product between p and some functional of f. So we can think of this thing, at least in the interior of our interval, as sort of gradient of our function of functions here, which is pretty cool. In fact, at the end of the day, what we're going to see is that the fourth derivative equals 0. So it really is like taking the gradient and setting it equal to 0. Okay, so I'm a little bit low on space here. So I'm wondering if I should erase yet. Yeah, I'm going to clear out, and I'm just going to copy this formula here over to our expression so that we have a little bit of space on the right-hand side. So I'm going to remove our general definition and our equalities here and just put it on the left-hand side. Okay, so all I did was move the formula that we proved over here. Okay, so now we're going to do the magic of variational calculus, right? I mean, so far we just derived a complicated-looking formula for the Gateaux derivative, which is nice, but not super useful quite yet. But now here's going to be our little piece of logic that gets us there, which is as follows. So again, we're going to, in this class, make smoothness assumptions with abandon. So we're going to assume that f is smooth, differentiable, whatever we need here. But in any event, suppose that f here is optimal for our optimization problem. Well, now let's think about this directional derivative. If f is the minimum, and I perturb f, right, then essentially the energy has to decrease, or increase rather. So in particular, what we can convince ourselves is that in this case, we know dEf of p is equal to 0, right? The directional derivative is equal to 0, but with a caveat, right? So long as the function f of t plus hp of t satisfies the constraints. Now, what do I mean here? Well, remember that we're not just considering any old function as input to our energy. We only care about those functions that go through a and b and have the prescribed slopes at those two places. Okay, so since f is optimal, right, in particular, remember what that means. That means that f of 0 equals a, f of 1 equals b, f prime of 0 equals c, and f prime of 1 equals d for our input constants a, b, c, and d. Well, now our perturbation function, right, f plus h times p as a function of t also has to satisfy these constraints. In particular, what does that mean? That means that p here had kind of better leave this boundary information alone, right? So for example, if p of 0 is equal to something other than 0, right, then as I perturb f by p, it no longer satisfies our first constraint here. And if it no longer satisfies our first constraint, it could be that we could decrease e. Like for instance, maybe we just move b down, so that it's easier to draw a straight line between a and b, or we adjust the slope or something like that. But in any event, well, the only perturbations that we care about are those that preserve the constraints. But since f already preserves the constraints, essentially what that means is that we need a few conditions on p, namely p of 0 equals p of 1 equals p prime of 0 equals p prime of 1 equals 0. Right? Because otherwise, if any of these conditions is violated, then when I perturb and construct this function here, then either the value or the derivative at 0 or 1 is going to violate the constraints. Okay. Well, under this assumption, which is still a giant space of functions p, by the way, it includes all kinds of different functions, well, in that case, we can actually write an alternative expression for our Gateaux derivative, because take a look. Essentially, our boundary terms involve p and p prime, and those are all equal to 0. So what do we get? We get that our Gateaux derivative for this particular choice of p is really just 2 times the integral from 0 to 1 of the fourth derivative of f multiplied by p of t dt. Okay. Well, now we're cooking with gas, right? I mean, this is a really nice expression. Okay, so what do we know? We know that this expression, right, this directional derivative or Gateaux derivative, variational derivative, whatever you want to call it, is equal to 0 for a huge pile of different functions p. Right? Like essentially any function p that satisfies these 4 conditions can be plugged into this expression and out pops 0. And this includes a lot of really crazy looking functions, right? So for instance, one thing that I could do would be, so here's 0, here's 1, this is the t-axis. So p of t, has to equal 0 and have slope 0 at 0 and 1. But other than that, it has no other conditions. So for example, one thing that I could do is choose some t naught between 0 and 1 and construct progressively more pointy functions p, right? So like there's 1, there's an even pointier 1, there's an even pointier 1. And in each of these cases, when I integrate this function against the fourth derivative of f, I get 0. Okay? Incidentally, if I take a limit as things get really, really pointy around t naught, I get something that isn't really a function but a measure. It's called the Dirac delta function, which I think is familiar to many students who've taken electrical engineering courses. But if you haven't, that's okay, because it doesn't really matter. The basic point here is that if I think of this expression as kind of like a dot product, what did we do? We said that the dot product between the fourth derivative of f and just about any choice of p, so long as it satisfies a pretty weak condition at the boundary, gives me 0. So think back to our finite dimensional logic from before, right? Essentially, what we did is we argued that if something takes its dot product with an arbitrary something else and gets 0, it had better be something else. The inside had better be equal to 0. And exactly that logic applies here. Because including in these p's, these functions which are essentially just focusing more and more around one value of f at t naught, is basically saying that, well, f fourth at t had better equal 0 at every single possible t. Okay, and that is the magic here. So essentially, the conclusion that we can draw, which admittedly, this is an informal argument I just made, which is to say, suppose that f is optimal for our problem, and smooth, and whatever other assumptions we need to make this work. Then if I perturb f in a direction p, as long as I conserve our boundary constraints here, well, I should get 0, right? Because this is like the directional derivative of our energy in the p direction. Well, we have an expression for exactly what that directional derivative is. It's basically the dot product between p, right? That's the direction in which we are perturbing, and the fourth derivative of f. So what do we have? We have that the integral of the fourth derivative of f against any p satisfying some pretty weak conditions the integral of these two things against each other is equal to 0, right? That's this 0 here. So the conclusion that we drew is that the thing that's being integrated against p had better equal 0, because essentially no matter what I integrated against that fourth derivative, I got 0. So notice that we managed to forget p altogether. Essentially, at the end of the day, what did we do? We said, suppose that f is optimal. We did all this variational stuff, and we drew the conclusion that the fourth derivative of f is equal to 0. Okay, and of course now we know that there's a closed order, expression. If things have fourth derivative equal to 0, then we really have that f of t is equal to, a naught plus a1t plus a2t squared plus a3t cubed for appropriate choices of a0, a1, a2, and a3. And notice that those are going to come from our boundary conditions, right? We have 4 boundary conditions and 4 unknown coefficients, so that works out perfectly. And that yields something called the Hermite spline, which the details don't really matter for this course. I mean, what really matters is the fact that the fourth derivative equals 0. If you remind me, I can give you a link to a 6837 lecture that starts with this expression and these conditions and then gives you the closed form a0, a1, a2, and a3. But that doesn't involve variational calculus. That's just some extra algebra. Okay, so in any event, oh, by the way, and notice that this is cubic, which is what we kind of expected. See, I said cubic all the way when I started. Okay, so this was a very slow calculation, but you'll see that the core of it was really only a few lines. I just wanted to talk you through every piece of logic in a lot of detail to give you a nice, friendly introduction to what it means to do variational calculus. So some of the key highlights here, just to review before I conclude our discussion here. Well, the first one is just understanding the basic setup of when we need variational calculus. Essentially, we need variational calculus when we're minimizing some energy, like E, but rather than inputting a point, our energy inputs an entire function. Right? We're trying to find a function that makes E as small as possible, where E is this abstract object that inputs a function, and in this particular problem outputs the integral of the second derivative squared. Now, what did we do? We said, okay, it might be hard to define a gradient here. Like, we'd like to kind of take the gradient and set it equal to 0. That's a little tricky, but one thing we can do is take a directional derivative, and that is the Gateaux or variational derivative that we defined here. So we took an arbitrary second function p, and we said, how does E change if I start with the function f and perturb it a tiny bit by adding a little multiple of another function p? And we found, by integrating by parts, a pretty nice formula. And this is something that happens often in linear partial differential equation. Essentially, you end up with something that looks like an integral just against our perturbation p, plus some boundary terms. And the boundary terms we can often ignore thanks to logic like what we have on the right-hand side. So really what we got was the inner product between p and some other object. And this is basically our notion of gradient. And we'll see that that really carries out, for example, when we compute the gradient of arc length, as it were. Now, to actually complete our optimization story, from here, it was pretty straightforward. The basic point is that if f is optimal, then this expression on the bottom left had better equal 0 for any choice of p that satisfies some pretty weak conditions. And we're going to make a tiny leap of faith in this course because we do lack a bit of the mathematical analysis to do it rigorously. It says, okay, well, if the fourth derivative of f, inner product with p, is equal to 0 for any p, well, then in particular, the fourth derivative of f had better equal 0. In your homework, it's perfectly fine to make that style argument. I don't need you to make a careful analytical one. The one that I made for you is perfectly fine. Well, this is a condition on the derivatives of f, and it tells us something interesting about our function. For example, in this case, it tells us that f is a cubic. So what did we do? We started with an optimization problem, and we essentially derived, at least informally, that local optima of this problem had better look like cubics in the interior of the interval from 0 to 1. They also satisfy this boundary information, so at the end of the day, you can actually fill in what that cubic has to be. Okay, so This was a bit long. I think the longer you stay in 6838, and I encourage you to stick with it, I know this calculation is tricky, the easier it'll get. This is one of these things that feels really abstract, but eventually will just be mechanical. So drop by office hours, ask questions on Piazza, and do follow through this particular discussion with a piece of paper in hand, and make sure that you can reproduce each step on your own. But with that, I'll see you next week.